on cryptographic protocols. We have one session before the coffee break and two sessions, two talks after the coffee break. Our first speaker is Kalikinkar Mandal, and we'll be speaking on practical single-pass oblivious aggregation and billing computation protocols for smart meters. Kalikinkar just had a kid, so he won't be able to attend online, so we have a recorded talk. Okay, and there will not be the option to have questions after the talk. So we can start?
Hello, everyone. Thank you for attending my talk. So today I'm going to talk about a single-pass oblivious aggregation and billing computation protocol for smart meter. So in this talk, first I'll provide a brief overview of a smart grid and advanced metering infrastructure. Then I'll introduce some cryptographic primitives that we need to construct our protocols. And then I'll also briefly talk about the related work. And then I'll present our protocol. And then I'll conclude my talk by mentioning some future work. So smart grid is a modernized version of the power grid. So in a power grid, the advanced communicating information and computing technologies are introduced. And also in the recent these days, there is a growing trend to introduce the industrial Internet of Things devices. And a smart grid has four different domains. One is that the power generation, power transmission, power distribution, and the consumer domain. And all these four domains are connected to the control center, where a utility provider connects all these domains for a secure and reliable operations. And advanced metering infrastructure is in the customer domain, where the key components in in the advanced metering infrastructure, the main purpose is to enable two-way information flow between smart meter and the utility provider. And this information flow is for collecting smart metering data as well as for the management as well as for managing smart meters. So there are various benefits of AMI. For example, an utility provider can better understand and estimate the need for the customers. So it helps utility provider to forecast the energy consumption of a particular area in a city. For example, if an utility provider collects data, energy consumption data from a particular area, and if they analyze it, then for the future they can anticipate how much energy should be provided to a particular area. So these type of insights basically help the utility provider to do the energy waste management, and also it helps grid efficiency. And from the customer perspective, the benefits are the customers can see the real-time energy consumption, and also they can get the real-time billing. And these days, the time of use tariff-based billing is popular. That means the utility bill is not fixed throughout the day. So in different hours of the day, the bills are different. So this way, the customer can wisely use utility to get cheaper electricity bill. And the smart meter deployment is happening worldwide. So the smart meter technology provides various benefits to utility provider as well as the customers through fine-grained data collection. And if one analyzes the power consumption data of a household, then they can find when the individual is present at home or not. What are the what different types of appliances the household is using, and also the power consumption behavior reveal their personal habit. For example, when they get up in the morning, when they go to bed, etc. So these poses various privacy threats. And in the recent years, so many data protection and the privacy regulation authorities have recognized the need for smart metering data privacy. So this includes GDPR, US Court of Appeal, and the Data Protection Act in UK. So these are the initiatives from the legal side. And to preserve privacy of the smart meter data, in the technical literature, the aggregate sum measure was introduced for the smart metering data. So instead of giving the fine grained data, so multiple smart meter, they aggregate their energy consumption data and provide that to the utility provider. So these aggregate energy consumption may help the utility provider for the electricity forecasting purpose. But on the other hand, for the fine grained billing, the each in every hours or in every half an hour's energy consumption data is required in order to apply the tariff-based billing. That means the electricity bill should be like to provide privacy in the utility data. The bill should be computed in such a way so that the utility provider would not know the actual the raw energy consumption. So in the crypto literature, so some techniques based on the zero knowledge proofs were introduced. So in this work, we are going to consider a smart metering smart metering system where there are basically three key entities. So a set of smart meters, so which you can see here. These are the set of smart meters, and we assume that each smart meter has an electricity monitoring device. So these days it is becoming very popular. There is a electricity monitoring device at the home, which is connected to the smart meter, and that displays the current energy consumption as well as the billing. And also the third entity is the utility provider, where the utility provider collects data from the smart meter and uses for various purposes. So we are going to, so in this work, we consider two fundamental tasks. One is that aggregation, smart metering data aggregation, and the billing and the tariff-based billing. And so here basically utility provider decides the tariff, like what is going to be the rate for a particular day. So that is decided by the utility provider, and this is a public information. This is sent to the smart meters. So we are so we considered two problems. So the secure aggregation, where we can actually view the smart meter energy consumption data as a time series data. So suppose we divide the day into L intervals, and for each interval, smart meter is producing the metrological unit in the smart meter. They produce a value. So for example, for the smart meter smart meter 1 produces these L values, M11, M12, and M1L. And so there are multiple other meters at the T1 time interval. They produce these these values, and the utility provider is interested in knowing the sum of these value, which is basically the which is in this column. If we view in form of a matrix, so this is the column, sum of these entries. So this is the aggregation. And we'll also consider the billing computation based on the tariff. So this billing computation is basically an inner product computation. So given the energy consumption data and L tariff values, then so this billing computation is basically the inner product computation. So we consider these two problems. So and we assume and we consider and in our system we consider the semi-honest adversaries. So we can think there are two types of adversaries. One is that the utility provider. So utility provider might be interested in learning the individual metering data, so which may violate the customer's privacy. On the other hand, the owner of a smart meter, who might be interested in tampering smart metering data to get a cheaper bill. So these are the two types of adversaries we will consider. So now, so one naive approach to provide privacy in the smart metering data is to run a secure aggregation protocol, which will compute the aggregate sum, and run another protocol oblivious or privacy preserving billing computation protocol to to provide smart meter data privacy. So this is a naive approach. But in this paper, we ask this question: so can we design a single bus protocol to compute the aggregation and billing in a privacy preserving way, where we want to use where each smart meter will perform a minimal number of operation. And as the smart meters are resource constant, so we want to have a minimal number of cryptographic primitives implemented on the smart meters. So this is the question we are going to consider. So before we look at our protocol, let's look at what are the existing work in the literature. So there were different schemes because the problem of the smart metering data aggregation, I guess it was, to my knowledge, it was initiated in 2010, and the first scheme was proposed based on the homomorphic encryption. Then within a couple of years, there were several several protocols or schemes designed based on stream cipher-like encryption, differential privacy, secret sharing based techniques, and also the combination of techniques like Diffie-Hellman key exchange, commitment scheme, pairing, etc. And also the aggregator oblivious encryption technique was also proposed. And then for the smart metering billing, there were the main idea for the in the existing literature, the main idea for designing smart metering billing is based on the zero knowledge proof techniques. And these schemes were constructed using the commitment scheme, for example, Patterson commitment scheme, and also the CL signature scheme based on the RSA modulus. And there are some other scheme proposed by the Molina Markham. So they proposed a billing scheme based on the ECC-based CL signature, bilinear pairing, and some symmetric key operations, AES, etc. And so that is one work. They consider the billing and the load monitoring application. So the load monitoring is application needs the aggregated value, but their scheme was based on the stream cipher-like encryption and the differential privacy. But in that scheme, they haven't considered the tariff-based billing. And one of the recent work by Chow et al. So they proposed a privacy-preserving cash payment scheme for the smart meters, where utility provider cannot infer a user's payment amount. So now we are before we present our scheme, let's quickly look at two cryptographic primitives which we are going to use in our construction. The first one is a message authentication code. So message authentication code basically has two algorithms. One is the MAC generation algorithm and a tag. So in this case, in our construction, we need the strong unforgeability under the chosen message attack security for a MAC scheme. And we'll look at the general definition of an aggregator oblivious scheme. So an aggregator oblivious scheme, so it's a cryptographic scheme where there are, and this concept was actually proposed by the Xi et al. And in an AOS scheme, there are n users, and each user has a private input, and each user also has a private key, so which is denoted by SKI, and each user encrypts their private input XI using the S key and using some public parameter, and it produces a ciphertext. And there is an aggregator who also has a private key, and aggregator basically perform some computation on the ciphertexts and uses its private key and some public parameter to compute this aggregated value, to compute this aggregated sum, which is basically sum of I equal to 1 to n xi, and there are n users. So this is, and for an AOA scheme, the indistinguishability under chosen plaintext attack security required. So let's look at one concrete example for such a scheme. For example, so here we are taking the Joe-Libe scheme as an example. So in the Joe-Libe AOS scheme, So, there are basically three phases. It has a setup phase, encryption phase, and aggregated decryption phase. In the setup phase, there is a trusted dealer who generates two primes, P and Q. They are almost of equal size and computes a modulus. Computes a composite modulus value capital N, which is equal to product of P and Q. And the setup algorithm also randomly samples secret keys and secret keys of length 2 lambda bits, and the aggregator has a secret key which is basically negation of the sum of all secret key values of the users. And the encryption algorithm basically encrypts the value xi as 1 plus xi times n, and the hash on t to the power ski mod n square. So this we can it's like a Pilier style encryption. So Pilier style encryption. And in the aggregated decryption, the decryptor basically receives the ciphertext and multiplies all of them and computes hash of t to the power sk0. So this is the secret key for the aggregator, and then applies mod n square and then minus 1 divided by n. So this x is basically sum of 1 to n. And the security of the GLEB encryption scheme is based on the decisional composite residuosity assumption in the random oracle model. So we introduce the notion of the authenticated oblivious encryption, because the main reason is that if we look at the property of an AOS scheme, these ciphertext has the malleability property. That means if I know a ciphertext, then I can create a valid ciphertext. So this is something undesirable in many applications. So this basically motivates us to add the authenticity of the integrity and authenticity of the ciphertext. So our construction for the authenticated aggregator oblivious encryption is based on the hybrid encrypt then MAC construction. So an AAOE scheme has three components, has three algorithms. So there is a setup algorithm, there is an encryption algorithm, and a aggregated decryption algorithm. The setup algorithm is so we assume that there is a trusted dealer who basically generates the system parameters and creates some public parameter and some private parameters. And the private parameters include a pair of AOA key and a MAC key. So for each user, the trusted dealer randomly samples an AOA key and a message authentication code key. And this pair of key is given to the user. And the aggregator is given an aggregation key, which is SK0, and all the MAC keys. So this is the setup phase. And in the encryption phase, encryption algorithm basically accepts a private input xi and some public parameter, and it accepts two keys, SK0, SKI, and the corresponding MAC key, KI. And it produces two outputs. It's a ciphertext and a tag. And then the aggregated decryption algorithm receives a bunch of ciphertexts and tag. And it also receives a aggregation key and the MAC key. And this algorithm outputs either the aggregated value or nothing. So this perp symbol is used to denote nothing. And for this scheme, so we need int CPA for the plain text and int and integrity on ciphertext for the ciphertext. So int CTXT for the ciphertext. So this is a general construction. So now we can realize this construction using any AOE scheme and any MAC scheme. So so this can be, so we proposed this in the context of the so just I would like to mention another point. So here we consider a hybrid MAC encrypt then MAC, where instead of using MAC, one can use also a public key algorithm like signature algorithm. So then then the scenario would be something like the sign encryption. So now for the AAOE scheme, so we need the int CPA security and the int ctxt security. So for that, and we can actually prove it. So if the AOA scheme has the int CPA and the MAC has soup CMA security, then the AOA is construction is int CPA and int ctxt int ctxt secure, and hence it will provide the int CCA security. So we are omitting the proof. So now now we are ready to present the present our protocol. So in short, we will call it OABC protocol. It's oblivious aggregation and billing computation protocol. So here our idea is to use these authenticated we use that AOA scheme to design a single bus protocol where we can compute both aggregation and billing. So here our idea is that there are actually three entities in our system: smart meter, an electricity monitoring device, and the utility provider. So we shared the key in such a way so that the utility provider cannot learn the individual metering data, and the utility and the electricity monitoring device, which is located at the customer house, should not alter a AOE ciphertext. So this is the fundamental idea. So the smart meters has the AOE key and the MAC key installed in their HSM. And if a user tries to tamper the smart meter, then it will basically blow up. So in that case, we assume that user cannot tamper the smart meter. But on the other hand, user can tamper the ciphertext, because the CTI is received the user can actually intercept the ciphertext and can try to tamper. But here the intuitive idea is that if user tries to tamper an AOE ciphertext, then the corresponding MAC then it would be, for a secure MAC algorithm, it would be hard for the user to forge the tag. So now, in our protocol, there are basically two main phases. One is that one is the key setup phase, which is the initial, and this needs to be done only once. And in the key setup phase, there is a so this explanation is based on the JL AOA scheme, but it can be generalized for any AOA scheme. So the utility there is a trusted setup who generates two large prime P and Q and computes N, and it also generates the AOS key for each smart meter and a MAC key. And then the smart meter stores this SKI and the MAC key in the HSM, and EM device holds the SKI. This is the AOA key. AO is encryption scheme's key. And the utility provider holds the secret key or aggregation key and all the MAC keys. So now in our protocol, suppose at the tth time interval, smart meter has its meter reading Xi, and smart meter runs the AOS key encryption scheme, and it gets two values, an AOE ciphertext and a tag. And then the smart meter sends this pair to the EM device, and then the EM device decrypts the ciphertext and store Xi, and these Xis are used to compute the bill, and forwards the AOE ciphertext and the tag to the utility provider. And utility provider collect such tags from the different smart meters, and utility provider first verify. So when at the time interval delta t, when the utility provider receives total n such tags, then it first verifies all the tags on the using the ciphertexts. And if all the verifications are correct, and then it computes them, then it applies the AOA decryption to get this aggregated value. So this gives the utility provider the aggregated value. And to compute the bill, the aggregated divider, in, let's say, for example, in every lth time interval, the utility provider receives a billing key from each EM device. So, for example, if we instantiate our protocol using the JL AOA scheme, then the ciphertext, then the aggregation is computed as it multiplies all the ciphertext and computes H delta T J to the power negative SK0. minus 1 divided by n. So this will give the aggregated value. And for the billing key is basically, its billing key is computed using the secret key of the AOS scheme. So which is, these are the public value. It's a product of h of delta t, small delta t j to the power tariff value. Capital T is the tariff. So this blue color is basically some public information, and the billing key is computed using the secret key. So now, we can prove. So the security of our protocol is based on the security of the AOS scheme, and we implemented this. Now we implemented this protocol. In C++ using the GMP library, where we use the GMP to implement the JL AOS scheme. And we also implemented, we use ASCON to realize a MAC scheme and a hash. So we use ASCON MAC and ASCON XOAB, and hash in the XOAB mode, extendable output function mode. And we implemented it using the SIMD instruction to achieve the best efficiency. And then we perform experiments for the 128-bit security level. And for that, we chose a modulus of size 3072 bits. And we also chose the ASCON's parameters accordingly. And so according to our experiment, so we first did some benchmarking for 500 users. So how much time it takes to perform the encryption and decryption by the AAOE scheme. For example, if we have 500 users, then it takes about the 19 seconds to perform all the encryption. But anyway, in the real world scenario, because this computation will be done in the distributed manner, because each smart meter will perform one AAOE encryption, and the decryption will be performed by the utility provider. So to perform decryption, so it takes around 47 milliseconds, and we also computed we computed the aggregate sum for 500 users. So there is another. So we've had it. We perform experiment for different smart meter. For example, 5,000 smart meters. So the time required. So here basically the smart meter computation is distributed, and the utility provider computation is performed at a central place. For 5,000 smart meters, so the aggregate sum computation takes about 112 milliseconds. 122 milliseconds, where the 42.62 millisecond is for the tag verification, and around 80 millisecond is for the JLAOE decryption, aggregated decryption computation. So we also compare our work with the protocol which are closest to ours in the literature. And we compare with the billing scheme. We compare with several billing schemes and some aggregation scheme based on AOE, and we see that there are different schemes they used signing. They have the signing algorithm, commitment, hash and ECDA signature, etc. And if we compare with them, then we see that for our scheme, where we can achieve both aggregation and billing functionality using only two primitives. One is AOE primitive, and the second one is if we have a permutation-based primitive supporting both MAC and hash, then we have one primitive. So we need only two primitives. So only with two primitives we can support both aggregation and billing protocols. So which is better compared to the other protocols in the literature. So now I'll conclude my talk. So in this work, basically, we introduce a new notion. It's called the authenticated aggregator oblivious encryption scheme, and these schemes can be realized with existing AOS schemes. And we presented one single pass protocol. So because we also have only billing scheme that can be designed using the AOS scheme, which we omitted here, and we presented only the only the aggregation and the billing protocol together in this work. And we also have shown that our protocols are secure against the semi-honest adversaries. So this is our preliminary work, and so here I have been extending the constructions, and also we are working on the implementation for the 32-bit ARM microcontrollers, which are used in many modern smart meters. And this work was supported by the NB Power Cybersecurity Research Year grant. And thank you very much.
Okay, so I guess we ran out of time, so we have to cut him off. Yeah, as I said, there's no opportunity for questions. You can send him an email to the speaker if you wish. And since we're running a bit behind schedule, we'll resume at 11:15 instead of 11. Okay?